Okay, in this video I'm going to discuss strategies for identifying and managing issues of multivariate non-normality in the context of structural equation modeling. The example is actually derived from chapter 12 of Barbara Burns' book, Structural Equation Modeling with AMOS. And you can actually go to this website right here and download the data set, and that should be, that's where you can get the data and follow along if you want to do it a little bit more closely using her book. It's a really good book, so I certainly encourage folks to consider it. Okay, so we have a confirmatory factor analysis model that she presented in chapter 12. These are items from the Beck depression inventory, and you can see that we have essentially a second order confirmatory factor analysis with these items loading onto first order factors, and those first order factors in turn loading onto a second order factor. We also have correlated errors associated with a couple of the items. So at any rate, the way that she laid out chapter 12, she essentially, what we're going to find out as we go through this is that the items themselves exhibit a lot of univariate non-normality, and also we're going to see that they exhibit multivariate non-normality as well. And so we have to keep in mind that in the context of SEM, most SEM programs utilize maximum likelihood estimation by default, and this estimation approach makes the assumption that the variables included in your analysis exhibit multivariate normality, and so violations of this assumption can lead to inflated chi-square test values, and it can essentially lead you sort of down the road of trying to respecify a model that otherwise would be good fitting if we weren't violating that assumption. And so it can lead you to model misspecification if you end up trying to respecify the original model. Secondly, it can lead to a tendency to underestimate standard errors, and that can yield incorrect inferences, such as and basically you end up making a type 1 error when it comes to model parameters. So although univariate normality is a necessary condition to achieve multivariate normality, it's not sufficient. So in other words, your variables can exhibit univariate normality yet fail to achieve multivariate normality. And so for this reason, you really should pay attention to both of these issues. So AMOS allows you to assess univariate normality and also multivariate normality in a couple of ways. So you'll see in this slide right here, I've gone under analysis properties and I've asked for tests for normality and outliers. And so here's our model, and I will just kind of go through and run the analysis. So you'll see that I've got my data here, or my model up. Under data, I've got the data set that I've imported. I've basically downloaded from the website and imported it into SPSS. So if you just want to take a quick look at the raw data, this is it right here. So these are the Beck depression inventory items. So under analysis properties, I'm going to go to output, and I'm going to ask for tests for normality and outliers. And so typically I could ask for a number of other things, but I'm just trying to illustrate dealing with normality or lack thereof in the context of SEM. So I'm just going to click on that for this demonstration. Also note that if there's any missing data in the data set, then I'm not going to be able to obtain this. So the fact of the matter is that if there's any kind of missing data, this kind of goes out the window in terms of me being able to assess for the presence of non-normality or the presence of outliers. So if you have missing data and you're going to utilize something like the full information maximum likelihood as approach, you'd have to actually click on this. But if I end up doing that, then I'm not going to be able to get the normality information. So what you'll need to do is you'll need to manage the missing data problem before you even try to do this. So you may end up utilizing something like list-wise deletion or some kind of imputation strategy, but you need a complete data set in order to obtain the normality information. So I'm just letting you know that. So the data set that I have right here actually has no missing data, and so I'm just going to go ahead and run the analysis based on that. Okay, so I think, let's see, I was just kind of messing around with this earlier. So at this point, what I'm going to do is I'm going to run the analysis, and when I click on the output box, you'll see that I get assessment of normality and then Mahalanobis d-squared values. So under assessment of normality, what I get are skewness and kurtosis values, as well as a critical ratio for each of those. So essentially, you can look at the critical ratio as z-scores or z-values. And if you wanted to test the statistical significance related to skew or kurtosis, then you can do that. So if you use conventional 0.05 level, then what we're looking for are essentially a critical ratio that falls outside of the range of -1.96 to +1.96. So if the value falls above 1.96 or below -1.96, then you would have a statistically significant test statistic. And what that translates into practically would be that the null hypothesis is that our distribution is not skewed and does not exhibit kurtosis. Or at least it does not demonstrate sort of a platykurtic or elliptikurtic type of distributional shape. So if we find statistical significance for either of these, then we're essentially going to be concluding that there's evidence that the data is departing significantly from normality. Not exactly sure why they don't just go ahead and give you p-values in here, but that's how they set it up. So at any rate, you can see that really all of our critical ratios, these are basically for univariate tests of skew and kurtosis for each of our variables in the data set. So you can see pretty much all the way down the line in terms of the test for skewness and the test for kurtosis. All of those would be deemed as statistically significant at the alpha 0.05 level. Now, one of the downsides of utilizing test statistics like this in the context of SEM is that because SEM is a large sample technique, it's often you can easily find yourself rejecting the null and concluding that there may be more substantial departures from normality on these dimensions than maybe there really is. So you have to keep in mind that whenever you're testing assumptions, those assumption tests are impacted by sample size, which can increase the power of your test and end up rejecting a null when perhaps maybe there's not much of a deviation from the null. So you do want to kind of keep that in mind. So I'm just kind of going back, look at my little slide right here. This is just kind of refreshing you on that the critical ratio column are basically z values, and so you can use that sort of threshold for the 0.05 for testing significance of skewness or kurtosis at the 0.05 level. Just look for a critical ratio that falls between a -1.96 or positive 1.96. If the critical ratio falls kind of in this range right here, then we would say that we're not departing from normality on that dimension. But if it falls below -1.96 or above positive 1.96, then we would conclude that there is evidence of a departure from normality. But as I said, those tests are impacted by sample size. So Klein actually suggests, or actually Barbara Byrne and Klein kind of give some thresholds for deciding on departures from normality. In her book, Byrne suggested maybe a value on kurtosis that's greater than 7 might be indicative of a more substantial departure from normality. She kind of used that threshold. For Klein, he cited Curran et al. And suggested that kurtosis values that are really kind of really 8 or above would be indicative of more substantial levels of kurtosis, which can be problematic. He also suggested that skewness values greater than 3 in absolute value may be indicative of more extreme levels of skew. Although, really the skewness, I've seen various rules of thumb between -1 and +1 would be consistent with normality. Some people would adopt, thresholds of -2 to +2 on skewness, but there seems to be less of a consensus with respect to kurtosis. But it looks like in general, at least according to these authors, kurtosis values greater than 7 or 8 or above would be indicative of departure from normality. Now, Byrne also suggests that kurtosis probably is more relevant to the question of multivariate normality or lack thereof than skewness, at least in the context of SEM, because kurtosis impacts tests of variances and covariances, whereas skewness has a greater impact on means. So, at least my read of her discussion is that really we ought to be placing a little bit more emphasis on assessing kurtosis rather than skewness in the context of SEM. So that probably also will explain why in the AMOS output you'll notice that you'll see the multivariate kurtosis provided down here rather than any other kind of multivariate normality tests. Okay, so it does appear that all of the variables in this data set exhibit significant skewness and kurtosis. Really using both approaches, we can see that there seems to be, in large part, substantial departures from normality on skew on a number of these. You do have a few of these where there's not as much departure. Using the Klein's 3 in absolute value for skewness, you can see that these variables would be consistent with normality, whereas you've got this variable right here, and this variable exhibiting more substantial, and this variable exhibiting more substantial skew. When it comes to kurtosis, you can see that these variables exhibit more substantial kurtosis. This would meet the threshold. This would meet the threshold. In terms of the critical ratios, though, again, all of these are really statistically significant. So really, it looks like we have a lot of problems with respect to deviations from normality at the univariate level. The multivariate kurtosis that's provided, as I said before, there are various rules of thumb. This is still a critical ratio, and we can still use this, treat this as a z-value, and use we can say that values that are less than -1.96 or greater than +1.96 would be indicative of the presence of multivariate non-normality. So that would be the case here. And then Byrne also suggested that multivariate kurtosis values greater than 5 can be treated as indicative of departure from multivariate normality. And so that's clearly the case right here. Okay, so we can also assess the presence of multivariate outliers. And so really what we're talking about is that if we were to plot our variables into multi-dimensional space based on the number of variables that we have, you can imagine that there would be an intersection of the means of all of those variables. And that is basically referred to as a centroid. And so what we're looking at is the deviation. If you can imagine sort of a data swarm for all of our variables, with the centroid sort of lying in the middle of it, we can look to see or calculate the distances between each observation and that centroid. And so the basic idea is that if the difference is deemed as statistically significant, that would be evidence that you would have presence of a multivariate outlier. So it's a similar notion to what we see in the context of assessing univariate outliers, but in this case we're looking at outliers in relation to all of the variables in the data set. So essentially the distance measure is called Mahalanobis distance, and actually we square that distance value, and we know that the Mahalanobis distance is distributed as a chi-square statistic with the degrees of freedom equal to the number of variables. So we can actually test the Mahalanobis d squared or distance squared using conventional statistical significance testing. I will say that Klein recommends more conservative p-values such as a p less than 0.001 to assess for the presence of multivariate outlier. So in the AMOS output, if we look, I'm going to go back to the actual output, and you can go to observations, and you can see farther is from the centroid, Mahalanobis distance. So we got Mahalanobis d squared, and we have two columns. We have a P1 column and a P2. So essentially the P1 column is really driving at the question of, is the case significantly different from the centroid? Okay, so is there a significant departure from the group centroid? And so the Klein reference really is kind of pertaining to this column right here, and you can see that all of the cases actually end up being statistically significant. And so obviously you can't have every single case being an outlier. So essentially what that translates into is that it's not particularly useful in this context for to use this test to assess the presence of an outlier. Now, Barbara Byrne talks in her book about that you can also she says that a multivariate outlier will tend to be one whose Mahalanobis d squared values depart substantially from the others in the data set. And so when you're looking at this data set right here, you can see that really for the most part the Mahalanobis d squares seem to kind of creep downward. Okay, and so in AMOS these values are presented in descending order. So the highest value is here, and then we have decreasing values, and so you can see that they seem to creep down, but you can see that there seems to be sort of a break point right here between observation 886 and 389. This is a large data set, so that's why we have so many. And so it would appear that there would be some evidence that maybe case 886 is a multivariate outlier. So one option might be to delete the offending case, or you could run your analysis with and without to look to see if including or excluding it has an impact on the results. But that might be a candidate as an outlying case. Okay, so the P2 column contains p-values that are used to test the likelihood that the ordered values of n being as far or further away from the centroid. And so I've actually got a little site right here. And so Byrne states that these values or the values in the P1 column are oftentimes expected to be smaller than those that are in the P2 column. So I'm mainly focusing in on using the P1 column, but the P2 column could be used kind of in conjunction to also evaluate the presence of outliers. All right, so ways of dealing with non-normality. All right, so if your data exhibit non-normality, there are a number of strategies that you could adopt. One is to simply try to go through and detect and manage outlying cases or variables that fail to exhibit univariate normality. And so for instance, I might look at the data set to evaluate the presence of univariate outliers, and again, maybe consider deletion or other strategies for dealing with severe departures in normality. Might be transformation of your variables, that sort of thing. So like a log transformation or square root transformation, things of that nature. So essentially just kind of handling things at that level. Now, another option is to use an estimation method that does not assume multivariate normality. So we said that maximum likelihood estimation assumes multivariate normality. If that assumption can't be met, then you might try a different estimation approach. But the problem is that a lot of these other estimation approaches have some serious limitations. One recommendation by Byrne was the ADF estimation. And she states that it's not really recommended with cases really less than 1,000. You're really shooting for a number of cases that fall at least at 1,000 and greater. Another option is to use a corrected test statistics and corrections to standard errors, such as the Sator-Bentler scaled chi-square statistics, so forth. Unfortunately, this is not available through AMOS, so that really creates a little bit of a problem. So one other option is to use bootstrapping, which is actually available through AMOS. And so um, you have essentially a couple of areas to consider bootstrapping. One area, remember what I said before, that um, you know that when it comes to estimation, maximum likelihood assumes multivariate normality. And so one of the effects of a violation of multivariate normality is to increase the chi-square value um, uh, based on your that's computed from your model. And what that translates into is that it's more easy to reject your model and conclude that it's a poor fit to the data when you have violated that assumption. And so then that can kind of lead you down the road of trying to retool or respecify the model to improve the fit, and that can be kind of a problem. A second effect is that it impacts the standard errors, and essentially what it can do is it can drive down standard errors within your model, and you end up having an increase in the likelihood of type 1 error. So we really want to consider options that address both of these issues right here. So one option with respect to the generating appropriate standard errors, or at least more reasonable standard errors, is to use nonparametric bootstrapping in AMOS. And so you can see right here I've got the analysis properties box open, and I'm requesting bootstrap samples and bias corrected confidence intervals. I've also clicked on bootstrap ML. And so what this is going to do is it's going to generate standard errors, bootstrap standard errors for your estimates, and then confidence intervals that are bias corrected. And so that will kind of deal with this issue right here. Now, it doesn't really deal with the issue of the inflated chi-square values. So in this case, what we can use is still bootstrapping, but we can use the Bolenstein bootstrap right here. And so I'm going to demonstrate both of these. Keep in mind that bootstrapping essentially involves taking repeated random samples from your data. The sampling is with replacement, and the idea is we generate a new sample that is of the same sample size as your original sample. We compute our test statistics and our parameter estimates from the bootstrap sample, and then basically that information, we're essentially treating our sample data as sort of a pseudo population. And so we take out repeated samples, we compute our statistics and so forth, we replace, and we just keep kind of doing this over and over again, in this case 500 times. Remember that each sampling though is technically with replacement, so each observation is replaced before the next sampling. Okay, so let's do this. So we have our model right here. So I'm going to click on this little button right here and go to Bootstrap, and I'm going to click on Perform Bootstrap Bias Corrected Confidence Intervals, and I've got it set at 95%. The default is actually 90%. I'm not sure why they stuck with that, but that is I just increased this here. The default for the number of bootstrap samples was 200, and I just raised it to 500 right here. And then I'm also going to click on Bootstrap ML, and now I'm going to run the model. So you'll notice that when I click on this button right here, you can see I've got bootstrap distributions, bootstrap iterations, and so forth. Click on estimates, And then scalars, you'll see I've got regression weights. And now when I click, so this is, these are based on, these are the maximum likelihood estimates. These are the parameter estimates themselves, the factor loadings in this particular model. The standard errors that are based on the maximum likelihood estimation, the critical ratio, which are z-values, and then the p-values that you see right here. Now you'll notice that if I click on, so this is under estimates right here. If I want to get the Bootstrap standard errors, I can click on this button right here, and so these are the Bootstrap standard errors. And so it's essentially, we've taken, we've generated Bootstrap standard errors for each of these parameters for 500 samples and computed the average of those, and that gets us this value right here. So you'll notice that these values in large part are going to be, in this case, they're larger than the standard errors that we had with respect to the maximum likelihood estimation. So we're correcting those standard errors. You'll notice too that this standard error right here, it looks like it's a 0, and we have a 0 here. There are no these aren't zeros in the sense that there's, the reason why these are zeros is that in our confirmatory factor analysis model, we fixed 3 of our factor loadings to 1, and this was used to scale our latent variables. So so that's the reason why those are there. So the zeros really just reflect the fact that no standard error was estimated for those because we had fixed those parameters to 1. The Bootstrap confidence interval, you can see right here, we've got our original estimate that we had in our previous table, and then we have the 95% confidence intervals for each of our variables. So you can, basically the null hypothesis is 0. If 0 falls between the lower and the upper bound, we would maintain the null. If it falls outside, then we reject the null. So you can see right here we are rejecting the null, rejecting the null, rejecting the null here. Again, this coefficient was fixed at 1, so that's why there's nothing right here. And you just interpret all the way down. We also have p-values that are presented if you want to consult those, and so you would interpret the p-values the same way you would in the previous regression table. So these are essentially the standard. These are the estimates, and then essentially we're computing the confidence intervals and the p-values after adjusting the standard errors, which I showed you in this table right here. So these are the standard errors that were utilized. Okay, so at this point, let's just take a quick look at the model fit. You can see that this is the chi-square value based on our data. You can see that there's the CFI, the RMSEA. Really, a few of these things aren't too bad. TLI is on the low side. Some of these other values are on the low side. But to utilize the Bollenstein, what we're going to do is we're going to go to Analysis Properties, and we'll click on Bollenstein Bootstrap. Now the deal is that unfortunately we can't click on this and get the bias corrected confidence intervals and standard errors and so forth at the same time. It's really kind of a nuisance. But so I'm going to click on this. I'm going to click off of this and this right here, and I will get the Bootstrap samples, and we'll evaluate the fit of our model using that. So I'm going to leave the Bootstrap clicked right here, and when I calculate the estimates and go into this box right here, you'll see it says Bollenstein Bootstrap. If I click on this, you'll see the number of iterations and the sampling approaches, basically the 500 samples that were generated. It says 500 usable Bootstrap samples were obtained. So our estimates are derived from the complete set of 500 Bootstrap samples. You'll see this is the distribution of the chi-square values associated with each of those Bootstrap samples. So there's 500 cases right here, and so our 500 bootstrapped chi-square values, and so this is the distribution. Now the model fit, this was the chi-square value from our model, and these are still based on the maximum likelihood estimates. So you'll see it's 717, and when we go into look at this distribution right here, if we plot our 717 for our observed chi-square from our data, it's actually falling out here in the upper tail of this distribution, which means that, you know, really all of our bootstrapped chi-square values actually fit the data better than the chi-square from our original sample, and that actually is not a good thing, in the sense that what it indicates is that our model is not really doing a good job of fitting the data. So if we go to this button right here, Bolenstein Bootstrap, you'll see that it says we get a p-value. And so basically, just to really simplify things, what we're looking for, if your p-value, you know, is less than or equal to 0.05, the kind of the standard threshold, then we reject the null hypothesis, reject null. The null being that the model is correct. So if the p-value, which we did obtain, is 0.002, if it's less than 0.05, which it is, then we're going to reject the null hypothesis that the model is correct. And really what that tells us is that we have a little bit more work to do in terms of specifying our model. So at any rate, this concludes this overview of you know, managing normality or lack thereof in the context of structural equation modeling.